Manager for the U.S. Army Corps of Engineers, Portland District, and along with me from the Corps of Engineers, I know I have Christy Johnson, who is also works in the Willamette Valley for the Corps of Engineers, and Ross Heiner, who works in the Portland District, Dam Safety Program Manager. Also, who else did we have from the Portland District on? John Morgan with our Public Affairs Office. Hi, John.
Hi, Derek.
Great. Hey, glad to have this good turnout. Looks like close to 30 people here. Intent today is to provide an overview of our mission in the Willamette Valley, talk a little bit about the South SANTIAM sub-basin, the facilities that we have there, talk a little bit about dam safety and some of the parameters around how we think about risk and how we manage it and what kinds of exposure people have in the South SANTIAM. Really glad to be here. This is an important subject, and in as much as it's important to kind of understand how this system works and where the risk parameters are, knowing the responsibility that and role that the local community plays and that you have as individuals in protecting yourselves is a really good thing. So information, knowledge is power, and we hope to be able to impart some of that today. Next slide, please. All right. Yeah, so I mentioned providing a kind of big picture overview. We'll talk a little bit about water management, and then dam safety program overview. We'll look at dam breach inundation maps. We'll talk about emergency action plans, and then building community resilience. Thank you. Next slide. So the Willamette Valley is comprised of 13 multi-purpose dams in the North SANTIAM, South SANTIAM, McKenzie, Middle Fork, Rao, Coast Fork, and Long Tom. And you can see by their, in order of the age of their completion, the dams in this particular system. 12 of them are on the east side of I-5 in the Cascades, or in the foothills of the Cascades, and one is in the Coast Range. That's Fern Ridge, which was the first dam completed. Last dam completed in the system was Blue River. It's really important to note that these dams are, they're all different. Some of them are very large, hold back a lot of water with a lot of head. 2 dams are close to 500 feet tall. That would be Cougar and Detroit. And they all work together as a system for providing multiple benefits, but principally it's flood risks that we manage with these facilities. And we'll show how we do that here in just a slide or two. Here's a little bit about our configuration, our operating scheme. So we have control centers for these 13 facilities in the north, the Mid-Valley, and then in the South Valley. In the South Valley, our control center is at Lookout Point. That means the other facilities, the other 8 facilities, are all remotely operated from Lookout Point. In the Mid-Valley, on the South SANTIAM, Green Peter is operated from Foster Dam. Foster Dam is our control center. In the north, Detroit Dam operates Big Cliff on the North SANTIAM. Next slide. So this chart has a lot of information in it. If you this particular hydrograph really is from or rule curve or water control diagram is from Fall Creek, but it is analogous to the rest of our facilities around the valley, the rest of our storage facilities. You see the conservation storage and the line that surrounds that blue conservation storage area. If you consider that the time axis, month of the year, is horizontal, and the storage elevation is the vertical axis, you can see that in November, where we are now, we should be approaching or at the bottom of our water control diagram. And that allows us more space in our reservoirs to capture temporary high inflows and store floodwaters and hold on to the water in the reservoir until tributaries downstream in the main stem Willamette until water attenuates, and then we can use that capacity that's gained over time to eliminate that flood storage and go back to the bottom in the wintertime. So we progressed from November, which is a high precipitation month, into December, also a high precipitation month, and then back over to January at the start of the year. And then beginning in February, the frequency and amplitude of storms and storm risk begins to diminish. And so at that point, depending on which reservoir you're at in the system, we typically begin refilling for the conservation season. So you can see the red dot on that refill curve. So February, March, April, we refill these reservoirs so that we have water stored for the summer months, which provide for water quality, water supply, fish and wildlife habitat over the course of the summer months, where we let out enough water from our facilities, from our reservoirs that's stored to support those purposes, while we hold back enough so that there are recreation benefits upstream. That's kind of our scheme for how we manage water. Pretty straightforward, but I know for people who are unfamiliar with the area, they see the empty reservoirs in the fall and in the winter, and even sometimes towards the end of summer, and they say, "Hey, why are you letting all the water out of that reservoir?" Well, it's purposeful in the fall, and that's to create that temporary flood storage. And it's also purposeful when we use that water during the summer months for other purposes that sometimes have competing demands, like fish and wildlife and water quality. In the wintertime, we produce big benefits for flood risk management. In the April of 2019 storm that we had just a little over a year ago, we prevented about $2 billion of damages to properties system-wide. And that's a pretty big deal. We'll talk a little bit about flows and what things look like in the South Santiam River Basin. So thanks, Ross. The South Santiam at Waterloo. Waterloo is one of our control points downstream of our facilities. And what we did is some modeling to show where water flows would peak if the dams weren't there and weren't doing their job the way that they did. The actual regulated flow is represented by the blue line, and it goes up above the action stage to flood stage, but it doesn't surpass flood stage. The computed unregulated flow would have peaked sooner and at a much higher amplitude, and it would have encroached into major flood storage. So that's just an example. The flood stage would have been 4 or 5 feet higher than what we observed at Waterloo, and that made a substantial difference in April of 2019. Next slide, please. All right. At Jefferson, very similar graph. You can see we had a double peak at Jefferson, where the actual regulated flow bumped up just over flood stage at the beginning and close to flood stage several days later. But unregulated, without the dams in place doing what we did, we would have bumped up at moderate flood stage. The flood impacts would have been much more significant. You know what was unique about this flood as well is we had this atmospheric river come through in April, and that's fairly unprecedented to have that quantity of rain come in when we're really in refill mode at that point in time. The system itself was already 2/3 full when we had, in some parts of the Willamette Basin, almost 10 inches of precipitation come in. It was a pretty remarkable event from that standpoint. Next slide, please. At Salem, the actual regulated flow didn't hit flood stage. The computed unregulated flow would have well surpassed flood stage and got bumped up against major flood stage. So fairly significant effect there on the main stem Willamette at Salem as a consequence of having all of the upstream dams. Next slide, please. All right, so let's transition over to dam safety. Our dam safety program, Ross Heiner, is one of the best in the business, one of the best in the nation from my vantage point, and I've worked all over the country with the Corps of Engineers. Ross does a fantastic job, and dam safety is really, really important for us. Understanding the condition of our facilities and managing those conditions to tolerable risk levels is really what we do, and Ross is in charge of that for the Portland District. So Ross, I'm going to turn it over to you for a conversation on dam safety and the rest of the presentation.
All right, thank you, Eric. Can you hear me all right? Okay, thank you. Well, good evening, everyone, and thanks for your time this afternoon, this evening, to kind of learn more about the Willamette Valley Project and the dams that comprise the Willamette Valley Project, and how, and kind of an update on where we are with our dam safety program, the condition of the dams, and some of our risk assessments. So dam safety is a team effort. You know, I'm part of the team, Eric's part of the team, Christy's part of the team, and the community downstream is all part of the team. It's a shared responsibility, and it's a shared responsibility because it's an important component to living with this infrastructure that we derive the benefits from. So these projects, as Eric described, are varying sizes and scales and shapes, and some of them are, very, very impressive structures. Green Peter, well over 300 feet tall. Cougar and Detroit dams, approaching 500 feet tall. These structures hold back a tremendous amount of water, and there's a tremendous amount of potential energy that's stored behind them at different periods of the year. And so it's a humbling responsibility to lead the program, but it's an important thing that we do to make sure that the dams are performing, as they're originally intended, and that we're monitoring their performance over time with inspections, with instrumentation monitoring, and our operation and maintenance activities. What we'll talk mostly about tonight is our emergency action plans, our updates, exercises, inundation maps, and our risk assessments, as well as some of our operation and maintenance activities that we've accomplished over the past 5 to 10 years. So starting off, to kind of, one of the most important things we can do to have safe dams, to have a good dam safety program, is to do the preventative maintenance, do the maintenance activities to ensure that the structures are able to operate as they originally intended, and that we learn and progress our knowledge and address deficiencies as they come up, as we learn about them in a proactive manner. And so one good example of that is the progress we've made over the last 10 years on spillway gates and the reliability of those spillway gates across the Willamette Valley. This chart on the right shows the 13 dams within the Willamette Valley, the number of gates, spillway gates. We call these tainter gates. They're radial arm gates that take the water load from this large skin plate, distribute that load across these horizontal members and into these strut arms, these big truss frames that put all that force into what we call a trunnion. And all that force in the trunnion is a door hinge. And so it's a lot of force, a lot of frictional potential for large frictional forces in this trunnion pen as you're opening and closing these gates. And so because these members are under a lot of stress, and these pins are under a lot of stress, you have to reduce that friction to as low as possible. And what we experienced and what we observed in some of our spillway gate climbing inspections, where we put climbers hanging from ropes on these gates, is that some of these members were starting to deform. They were starting to bow a little bit and get a little bit out of alignment, which was a warning sign to us that we needed to address something. There was a problem. There was a warning sign, and we needed to act. And so what occurred was that what we're observing is that these members were getting overstressed as we were opening and closing the gates under those, and friction was developing in those trunnion arms. And so over the last 10 years, we've systematically gone through and upgraded the structural, electrical, and mechanical reliability of almost all of our spillway gates across the Willamette Valley. We're still in progress. We've got some ongoing construction at Detroit, Cougar, and Hills Creek, and some follow-up work at Foster that's planned in future years as funding allows. And Will, I see your note there. It's supposed to have 11 dams shown. We have 2 dams in the south, in the Coast Fork, Cottage Grove and Dorena, that have spillways without gates. So it's an ungated spillway with if the water gets up to a certain level, it flows over that OG without having to operate gates. And so, yeah, we have 11 projects with gated spillways and 2 with ungated spillways. Eric's right on the spot there too. So you'll notice particularly interested tonight in Foster and Green Peter. Foster was actually the first project where we observed this problem, and one of the first projects we addressed with the structural rehabilitation. What we found in subsequent projects is that, yeah, we need to address the structure and strengthen the structure itself and replace the trunnion pins with self-lubricating, lower friction materials. But we also need to look at the reliability of the electrical and mechanical equipment that lifts and lowers the gates, so that when we go to push that button to open the gates, we have high confidence that it's going to open and we're going to release the amount of water we're intending to. And so there's some follow-up work that we are budgeting for in future years to come back and address at Foster. But we test those gates on a regular basis. We are operating those spillway gates quite frequently throughout the year, and so we have pretty good confidence that those systems will work when we ask them to. So that's the O&M piece. A big part of what the dam safety program has become over the last 10 or so years is really evolving from just inspections of our facilities into assessments of the risk associated with our dams, and everyone has kind of their own definition of risk, or it means risk means something a little bit different to everyone. Well, in dam safety, we try to be as quantitative as possible about risk, so we break it down into 3 important components. The simplest definition of risk that I've heard is something bad may happen, and really that's the best definition of risk that I've heard. It has all the components, some uncertainty associated with it, something bad may happen, and also, importantly, consequences, that bad thing that may happen. And so in the dam safety world, we're a little bit more detailed with our definition, and we break it down into 3 components: the hazards, the performance, and the consequences. So the hazards are potential for flood loadings or or earthquake loadings, or just the normal operations of the dams. And given those conditions at the dam, we look at the performance. How is the dam likely to perform? Is it going to perform well? Are there potential failure modes or problems that we might experience? And what's the probability? What's the chance of that bad event happening? And then importantly, the consequences. We're talking about dams that control a lot of volume of water, and so what we're looking at is the inundation of areas downstream. Who's downstream? What may flood? How much warning time? Those sorts of questions we ask in our risk assessments to try to come up with our risk classifications and prioritize our activities going forward. That could be either further evaluation of potential problems or physical fixes and repair of certain components that we're concerned with. And so our tools in our risk assessment toolbox kind of build up from this basic risk assessment we call periodic assessment that we do on a 10-year frequency. As I said, we implemented this new framework of risk assessments about 10 years ago. And so by now, at this time, we've performed one of these basic risk assessments of pretty much all of our dams across the nation, and including the 21 in Portland District. And so this routine risk assessment really prioritizes our work and where we need to do further evaluation. That further evaluation happens in these non-routine risk assessments called issue evaluation studies, of which we have several ongoing right now. And these are where we get a lot more detailed in our risk assessment. We become more quantitative, can include field investigations to test the materials that were actually constructed, do detailed analysis, and bring in some outside experts to help us better classify the risk and really answer the question, is there a problem that needs to be fixed with this dam? If the answer to that question is yes, and there's some risk that needs to be addressed on a permanent basis, we move into what's called a dam safety modification study. And this is a planning alternative study that looks at different risk reduction alternatives that will be implemented on a permanent or long-term basis. And they look at a variety of different things, changes to the operation, changes to the physical components of the dam, strengthening components, modifying components, expanding components, et cetera, and really try to come up with the most cost-effective and risk reduction alternatives to lower risk and reduce risk to acceptable levels. And so those are kind of the tools in our toolbox for risk assessments. And this is kind of a zoomed out overview of the Portland District portfolio of dams. You can see we have the three large dams on the Columbia River that we're responsible for, we own and operate, the projects down in the Rogue River Basin, and then the 13 dams in the Willamette Valley project, including Green Peter and Foster. So those are highlighted here. We have a risk classification, and this is really the way that things get prioritized within our program. We have 700 dams across the nation, and so these non-routine advanced risk assessments get prioritized on a national basis based on this risk classification. And right now, an update for Green Peter Dam. We just finished one of the issue evaluation studies, the advanced risk assessments, and it was upgraded from a risk classification 2 or high risk project to a classification 4 for low risk project. And so that's really good news, and it's a testament to a lot of the spillway gate rehabilitation work we've done and just some of the really advanced analysis that we had to do to look at the earthquake performance of the dams, or Green Peter Dam, to convince ourselves that it's strong enough and stable enough to withstand some of the most extreme scenarios that Mother Nature might throw at it in the future. We still have a study ongoing at Foster Dam. Right now it's classified as a high-risk project, and in the next year or two, we should have results and a path forward on what the updated risk classification is and what the next steps are, whether we are satisfied with the risk and it gets upgraded, or if we need to go into the next phase of a modification study. So more to come on that. As we learn more, we'll definitely share those updates with the folks downstream and our partners. So kind of an overview of Foster Dam, and then we'll talk a little bit more about Green Peter. Foster Dam was completed in 1968. It's comprised of a earth embankment on either side of a concrete spillway, which is near the powerhouse and the fish facility right here. It has a gated spillway with 4 Tainer gates right there in the middle that if you drive along the dam road, you drive right on top of those gates. Can't quite see them, but they're underneath you on that bridge there. And it's pretty impressive that those 4 gates can pass flows up to 195,000 cubic feet per second. So that's a tremendous amount of water that these dams were originally designed to be able to pass in some of the most extreme flood events. And so an important takeaway here that I want to share is that these dams were constructed for flood risk management as their primary purpose. However, dams are not, they have a finite capacity, and they cannot eliminate floods. There's potential, they're designed to reduce floods and reduce the probability and consequences of floods, but they cannot prevent floods, and they're actually designed to pass some very, very extreme amounts of water if Mother Nature someday brings that amount of flow into the reservoirs. And so just for some context on the capacity of that spillway, 195,000 cubic feet per second. The flood stage at Monroe is just about 20%, or just about 15% of that at 26,000 CFS. And so kind of talked about the advanced risk assessment that's ongoing. One important thing about Foster is that it's a relatively small reservoir, 25,000 acre feet for a drainage area close to 500 square miles. So it really has a very small amount of flood storage available in the Foster pool. And so the potential for flooding still exists with the presence of Green Peter and Foster dams. That's certainly true. So moving to Green Peter, kind of make a comparison on the drainage area and flood storage. So Green Peter, the watershed above Green Peter is about half of what's above Foster Dam, 277 square miles, and it has about 10 times as much storage in the reservoir upstream. And that's due to its height and its narrow river canyon that makes up the reservoir. 378 feet is maximum height, and has 2 spillway Tainer gates that can pass flows up to 110,000 CFS. And so there's that updated risk classification of low that was just updated this year. So we'll talk a little bit about Green Peter, and then we'll talk about inundation maps and emergency preparedness. Just thought this was important. We get a lot of inquiries from the public and concerned citizens that are at the dam, and just want to give a little bit of background of how Green Peter Dam is constructed and some of the observations you might make at the dam. So it's a concrete gravity structure. That means it's made of these giant concrete monoliths or blocks that are between 45 and 60 feet wide. So the width varies between 45 and 60 feet along the length of the dam going across from left to right. Sits on a rock foundation. They prepared the rock, stripped off all of the loose material, got to solid bedrock, and then built up these concrete monoliths from the foundation going up. It's got those 2 spillway gates, and it has 2 regulating outlet gates. And then we have 2 penstocks that feed 2 hydropower generators. And so this is looking upstream at the dam, kind of a cartoon version of what that what the plans look like. In an elevation view, looking upstream, kind of towards the northeast. So here is a section or a slice of that dam. If you were to take a knife and slice it through and take a picture, this is what you would see. You can see our summer conservation pool and our winter flood pool, approximately shown here, and those pool fluctuations that Eric described before. You know, our winter pools are down here typically, unless we're managing a flood event, and then it's summer. In the spring, these water elevations kind of creep up to our maximum summer pools up here, and our flood storage is limited just to a couple of feet. But then we have that conservation pool to augment or increase flows downstream. And then moving down into the concrete dam, so these monoliths are built in 5-foot layers and kind of just cast one on top of the other, mass concrete. And what happens is the dam itself, these blocks are resisting the loads from that water, trying to push it over just by the weight of the blocks or the monoliths themselves. So we call this a gravity structure. So it's using its own mass, its own gravity to resist those water forces that are trying to push it over. What's inside the dam, near the upstream face here in red, is these copper water stops. And these water stops were designed to, at the joints between those blocks, to stop any water from coming in or through the dam, just to create a nice tight surface. They're not needed really for the structural stability of the dam, but they are there to minimize the leakage through the dam. We have a grouting and drainage gallery down towards the base that collects any water that gets through those, or most of the water that gets through those water stops, and then any water that seeps through this grout curtain that was drilled into the rock between the concrete and the rock foundation below. That's called the grouting and drainage gallery. So it's kind of a hallway or a tunnel that goes through the dam that we use to inspect, and we use to monitor the performance of the dams over time. We have uplift cells and pressure cells that measure the pressure at the foundation and make sure that we're not getting excessive uplift or forces pushing up and trying to overturn the dam. And everything from the instrumentation looks good. And so what we experience, if you've been to the top of Green Peter Dam during the summertime or when the pools are elevated in a flood event, you'll look down on the right side of the spillway and see water exiting one of these joints where these copper water stops have become actually broken or torn apart. Copper over time corrodes, and as the dam flexes, fractions of an inch with temperature and water fluctuations, voids form in those water stops and have allowed water to exit the downstream face of the dam. And so this is a condition that we're definitely aware of and definitely monitoring, but is not something of immediate concern. We're not seeing huge increases in that flow, and we're not seeing erosion of the concrete surfaces. This is a view from one of our low pool inspections, and you can see that joint is fairly tight, but is allowing some water to exit through and pass through those joints. But from a stability and dam safety perspective, we're not concerned, but it's something we do keep a close eye on. Okay, so kind of a transition here to our emergency action plans and our inundation maps. Several of you may have been part of our public meetings that we had 5 to 8 years ago, where we initially developed updated inundation maps for all of our dams and had public meetings to kind of display those and share those with the public and the folks downstream. And so this is kind of an update to that, and we'll share and kind of give an update of where we're going with our inundation maps to make them more accessible and more transparent, give you a sneak preview of what that looks like. But first, kind of want to talk about what dam breach inundations are and what they are not. So they're part of our emergency action plans, and they're used for risk assessments to estimate consequences. And they're used at the local level with emergency managers to plan for local evacuations and response plans. So these are the existing maps that we have were created with data that's protected by Homeland Security regulations that have critical infrastructure that's printed on the maps, and so therefore they're official use only. And so distribution is limited to just official agencies, typically just emergency management agencies, and can't be generally shared with the public. They can be viewed if you contact your county emergency manager, or if you contact the Corps, we can give you some information about them. You can view them in meetings such as this, but generally these maps were intended not to be distributed to the public. That's kind of changing, and I'll talk more about that. And a good reminder here, these maps are based on extremely unlikely and severe dam breach or dam failure scenarios. These are not likely events, as we're, especially for, as we're learning more about our risk assessments, these we consider very extreme flood events, very extreme seismic events, and try to push the projects and push the dams in our analysis to their breaking point to determine what is the most extreme loading condition they can endure and perform satisfactorily from. So these maps show extremely large flood events, and they show kind of worst case scenarios if the dams were to fail in a very rapid and widespread nature. These maps are not flood insurance maps. They are not the 100-year or 1% the probability flood inundation maps that FEMA uses for flood insurance. They're not evacuation plans or response plans. That's a responsibility of the county and local emergency managers to take the inundation maps and develop their evacuation plans and response plans. And generally, they're not specific to a specific cause of dam failure. They're generally looking at a large-scale failure of the dam or a breach of the dam to cause a large flood wave being released from the reservoir. So that's kind of where we started. Over here, these static map books that are limited in nature, for official use only, shared only with some of our close local partners. But where we're going is a lot more transparent as an agency. So we have right now in the works a update to the National Inventory of Dams that is being beta tested right now and will be scheduled for public release in fall of 2021. So around this time next year, there will be a lot more information shared about Corps of Engineers dams within the NID, National Inventory of Dams, that will be publicly available, and will include inundation maps that the general public can access, zoom into, find their area of interest, and really be empowered with that data and that information to be risk informed and make preparation decisions for themselves and their families. So here is kind of a preview, or this is a update. This is a sample example zoomed out of what the inundation mapping will show for one of these unlikely scenarios of a dam breach of Green Peter Dam. And you can see there's two different scenarios here, one in red, which is you can see in the background, and one in blue with this hatch, which is a sunny day breach. So this is when, if there was a catastrophic failure of Green Peter Dam at its maximum summer pool elevation, that inundation is shown in blue, and you can see it's quite widespread and quite devastating, and very unlikely, very low probability, but something that, because of the potential for that, makes our job very important to make sure we're operating and maintaining these dams and assessing the risk and addressing those risks in a proactive manner. This red scenario shown kind of below that, that extends a little bit beyond the sunny day breach, is the maximum flood breach. So this is that probable maximum flood, this hypothetical Noah's Ark type flood event, if that were to occur in the Green Peter watershed and then cause the dam to fail or breach, what that inundation boundaries could be. Again, quite devastating, quite dramatic, amounts of flooding and water. Something that's very unlikely, but something that makes our job in dam safety and operating and maintaining these dams a humbling endeavor to make sure we're doing the things we need to do to ensure the safety of these structures. So the same types of maps for Green Peter here are shown for Foster. Again, Foster is a smaller dam in height and reservoir storage, so you can see as I go back that inundation boundary is quite a bit smaller because of that smaller amount of volume of water that's stored behind the dam. For folks in Lebanon, the arrival time after a breach of one of these projects, of one of these dams, would be approximately 2 to 4 hours. So some time, but not a lot of time to hear a warning and evacuate to high ground. So that little bit of time that would result in one of these unlikely scenarios means that we need to have up-to-date plans, up-to-date relationships and procedures with emergency managers so that we're all on the same page of who we're talking to in one of these scenarios, and that we have those plans exercised and ready to go in one of these unlikely events. So as I said at the beginning, kind of dam safety is a shared responsibility, and that shared responsibility goes from the owner and operator of the project, the local emergency managers, and county officials, and includes the citizens and the general public that lives downstream to be aware, to be informed of the potential hazards, and be prepared. So kind of going down here, our responsibility and role as the owner and operator is to maintain the dams in good condition, monitor their performance over time, exercise our procedures, and train our personnel in what to do if something does go wrong. And then have proactive and provide warning and communication with our local EMs so that they can initiate evacuations and spread the word out to the populations, to the general public, and affect those evacuations. The local EM roles and responsibilities are to develop those evacuation plans and procedures, and to monitor the flood warnings and watches from the National Weather Service in the scenario of flood events. We work very closely with the River Forecast Center and the National Weather Service to schedule the flow releases from our projects and coordinate that and input our information into their models so that the unregulated flow of the tributaries that don't have dams is combined with the releases of water from our projects, and the schedules of all of those. Those releases are up to date in the Weather Service and the Northwest River Forecast Center models. And so there's a link and some more information, I think, on the next slide. So as a general citizen and somebody that lives downstream of our projects or of a dam in general, is we be informed of the potential hazards and risks. I would say that flooding and dam breach are just one of several hazards that folks should be aware of and have plans to mitigate and respond to. There's wildfires, there's earthquakes, there's several natural and artificial hazards that residents and citizens are exposed to. And so the best thing to have is to prepare plans, for your home, for your workplace, where you spend a majority of your time, for two things: to shelter in place and to be 2 weeks ready. I think the quarantine and the 2020, the COVID-19 has led us all to be quite a bit prepared and self-sufficient at home. Being 2 weeks ready at all times in order to shelter in place due to an earthquake, an ice storm, any number of scenarios is a good thing to be prepared for. And then also have an evacuation plan or a go kit. Have your key things ready to go so that you can, if you are warned, if you go from a level 1 to a level 3 evacuation warning, you're prepared. You have what you need to get out and evacuate your home and get to safety. And so here's a graphic from the Oregon Emergency Management. What would you do 2 minutes, 2 hours, 2 days, 2 weeks after a Cascadia earthquake? Do you have the water, the food, the shelter, the plan? Is your family, neighborhood, community 2 weeks ready? So that's kind of a reminder And as we get into winter, thinking about these things and being able to develop those plans for sheltering in place and evacuating are definitely things that citizens can do to prepare. Some additional resources for people that live adjacent to the rivers and downstream of our dams. One is the emergency management and being 2 weeks ready for those hazards. Oregon Emergency Management has a good compilation of resources and plans to get yourself ready for multiple different hazards. The Willamette Valley Teacup site is linked here. This shows in detail what the water elevations are in the reservoirs, how much flow is being released, how much flow is coming into the dams, etc. If you're interested about the operations of our dams, definitely recommend bookmarking this website. And then probably the best place to go for updated flooding information is the Northwest River Forecast Center, which you can either Google or jot down this URL for future use. But you can zoom in to the map and you can show, it shows you a hydrograph of the control point or the gauge, USGS gauge that's near you on whatever stream or river you live next to, and we'll give you a forecast of what was observed over the last 7 days, and then what the forecasted stage and flow information is likely to be over the next 7 days. So that's a really good resource if you're interested about flooding information. With that, that's the conclusion of my presentation. Happy to use the remainder of the time to answer any questions or get some feedback. But I appreciate your attention and appreciate the turnout that we've gotten tonight. So thank you.
I see we have a question from Will Tucker about sending out the slide, or at least a link to the slide deck. Ross, can we, Christy, can we do that? Get that out to Wyatt King?
Yes, this is Ross.
Yeah, we can do that. Echo. We also have recorded this presentation, so we put that out on YouTube, and we'll send out the link widely to all who participated. Wyatt has he can put the link on all the Facebook pages where it was advertised, so we will get the video out, and maybe we can have the slides linked to it somehow.
Gotcha. Thank you. A couple other questions here. I see Daryl asked the question, why not fix the leaks when they're small? And Ross, can you take a swing at that one?
I can. Well, you can see the height of the Green Peter Dam on this slide here. It's over 350 feet tall, and so the repair that's required to stop the leaks requires drilling a very straight, narrow hole, hundreds of feet down in these joints. So it's an expensive endeavor, and it's something that's a little bit tricky to do. And so we have plans in place, or we have budget requests in future years to do that exact thing. But right now we're kind of at the mercy of our appropriations process in order to make those repairs happen. And in the meantime, we're monitoring the performance. We take visual measurements of the leakage at different pool elevations, and then have a plan in place to install a weir box to monitor the flow on a more quantitative basis. But good point, and it's on our list of things to do.
Yeah, and just to add to that, Ross, we have a number of other priorities through the system, and we're constantly elevating and addressing those highest priority issues. And we have a finite, not an unlimited amount of resources, so time and money and people. So we are attacking those highest priorities right now. For us, those are spillway gates and issue evaluation studies that help us understand our facilities and their performance better and the hazards better. And so those are ranked a little bit higher than repairing this water stop leak right now. I see another question from Abbott. Worst case scenario, what can we expect for water level depth at the Lebanon airport, for example, if one or both dams go? So Ross, do you have that figure off the top of your head, or do you have reference to a flood inundation map?
I do not have that information on hand right now or in my head, so I hesitate to throw a number out there at this time. But we can definitely follow up with Abbott if you provide your email address or phone number. I'll definitely get back to you on that.
If we're able to reach back to Wyatt, would you be able to reach over to Abbott and get that information, or to Live Longer Lebanon? You know that we'll follow up with that. Thank you, Wyatt. In 2021, when this information is available to everybody, you'll be able to get online and take a look at travel time and at elevation flow under various scenarios. So travel time, I know, Ross, you said earlier, 2 to 4 hours. And if I remember correctly, the elevation in Lebanon is not very high because the landscape flattens out pretty well. But we'll follow up with some definite information on that. And then I see also there's a question about can we highlight what can happen at Waterloo or downtown as well. And so we'll run those 3 scenarios. All right. Yeah, several questions on the same theme about elevation, travel time, and planning escape routes. I will say that we've got exercises, emergency action plan exercises, coming up throughout the year where we have conversation with local emergency managers and officials on what we expect to see under a variety of scenarios so that they're informed and prepared. I think next week or later this week we've got something with Marion County. Is that right, Ross?
Yeah, that's right. Marion and Lane County coming up, and then working with our partners in Lane County later in the year into next year.
I see Daryl has a question. Is there an estimate on valley drainage? And I'm not sure exactly how to interpret that question.
I can answer that next question there from W. Is it an inundation map if both dams failed together? And I would say that Green Peter maximum flood failure is probably the worst case inundation.
All right.
And it does include a failure of the Foster Dam downstream.
Okay, I understand Daryl's question. Time for flood to drain after a catastrophic failure. Time for it to attenuate. And I don't immediately have an answer to that question. I know typically it takes a while for floodwaters to subside because water is going places where it doesn't ordinarily go in a flood. So, Ross, do you have any information on that?
I do not, but typically it's fairly symmetric, the hydrograph, so the water would begin to recede fairly quickly. But yeah, you're right. If it flowed somewhere where it's not usually going, then it could tend to pond or in those locations.
So we've got some takeaways on specifics for inundation impacts and the assumptions around that at Waterloo, at the airport, and at downtown. And then thinking about what we might see post-flood attenuation under those extreme circumstances as well. We will wrestle with those questions and we'll communicate back to Wyatt King. I know that we are out of time at this point in time, and so I want to say thank you everyone who chose to attend this session. Hope that you have a better understanding of what our dam safety program is and what to expect. And let's see.